Here is a classic MCAT type problem. A particle is in circular motion in the direction indicated. It is in increasing speed. When the particle arrives at point P, what will be the general direction of its acceleration? You may want to pause and consider your response. Note, it is at ever increasing speed. When it arrives at P, of course, it will have a direction of its acceleration at C. Anytime something is in circular motion, it's going to have a component of its acceleration pointed towards the center of the circle. That's the centripetal acceleration. If it's at constant speed, that's the only acceleration that it has. But this particular situation, it's at increasing speed, so that it'll have a component at C, but because it has an increasing speed, when it is at point P, the direction of its velocity will be tangential to the circle, so it has increasing speed. A component of its velocity will be at E. Therefore, if it's increasing its speed, a component of its acceleration will be at E. So we have a component at C, a component at E, therefore the general direction of its acceleration must be D. It is somewhere between C and E. If they were to ask that it was moving in the same direction but with ever decreasing speed, therefore if its speed was ever decreasing, when it was at P, because it's in circular motion, it will still have a component of acceleration at C, centripetal acceleration, but when it is here, it will have negative acceleration, because if something is slowing down, if its velocity is decreasing, therefore it has deceleration, which is the same thing as negative acceleration. So at point P, it will have a component of its acceleration at A. So we would have a component at A and a component at C. Therefore, the general direction of acceleration would be B if it has ever decreasing speed. Simple harmonic motion. Let's consider a pendulum. So here's a simple pendulum, sort of like if you have a grandfather clock at home, as if. You know how there's a pendulum that swings back and forth in the grandfather clock, or just take a cord and attach a rock to it. And as long as the angle between the cord and the equilibrium position is small, then this will simulate simple harmonic motion, which is to say that if you were to take the mass, pull it up here, let it go, and so gravity will now act on the mass, and it will swing back and forth. Therefore, it is oscillating in a periodic fashion. That is the definition of simple harmonic motion. Now there's other things that simulate simple harmonic motion. Moving in a circle, which is periodic. And also, for example, if you have a spring and you attach it to a ceiling and you attach a mass to it, then you push the mass, then the mass starts to oscillate in a periodic fashion. That's simple harmonic motion. You don't have to attach the spring to a ceiling. You can actually attach the spring to a wall, and as long as the surface is frictionless, then if you push the mass will bounce back and forth with simple harmonic motion, a periodic fashion in which it oscillates. In all these situations, simple harmonic motion can actually be graphed as a sinusoidal wave, a sine wave. And the reason this can be done is, you can imagine it here, is that a sine wave So you start in an equilibrium position, then the sine wave goes up in amplitude, for example, goes up in amplitude, then it crosses the equilibrium point, then goes in amplitude, the same amplitude, but opposite direction. So the sine wave goes up in amplitude, crosses the equilibrium point, goes down, amplitude is negative, but it's the same absolute value of amplitude, same distance, opposite direction, and then it repeats itself. So that kind of sinusoidal description or graph explains or describes simple harmonic motion. Now, in terms of the equation that describes this simple harmonic motion, it is given by t, the period, is equal to 2 pi root L over G. This is L, the length of the string or cord, and G, of course, is gravity. So a couple of things. One, notice that mass is not even there. The mass is not there. And so it is not relevant to the equation as to what the period is going to be. Only is relevant is how long this cord is going to be. Again, this is, you're able to estimate this because the angle is small. Then it is also dependent on gravity. Usually, believe it or not, you don't have to memorize this equation for the MCAT. Usually, they'll actually give you the equation. So a typical MCAT question would be, if the length is quadrupled, so if you have 4 times the length, what would be the ratio of the new period to the old period? So if you have 4 times the length, then you have 4L. You pull it out of the square root sign, it creates a 2. So it's like multiplying this whole thing by 2. So you've doubled the period by having 4 times L. And if you quarter the gravity, G over 4, well then the 4 pops up here, it's 4L, so you have the same situation, you double the period. So there's just different ways to manipulate these variables L and G. But one thing to underline for you, if you see that they say multiply L by 1.69, 1.21, 2.25, this should have a Pavlovian response for you. In fact, anytime I see those kinds of numbers on the MCAT, right away I start thinking about square root, because you need to memorize the squares of all numbers between 1 and 15. So of course 10 times 10 is 100, right? And then 11 times 11 is 121, 12 times 12 is 144, 13 times 13 is 169, etc. Then you get 14 by 14, 196, 15 times 15, 225. That you should have memorized. Why? Because if you see on the MCAT, you have the square root of 2.25. Right away, that's square root 2.25. 2.25. They didn't choose that number for nothing. 2.25, 225, root 225 is 15. So root 2.25, 1.5. So those are the kinds of numbers. They can choose these odd numbers that seem odd, like 1.44 or 1.69, but if you know that the square root of 169 is 13, then you're laughing. Then you would say, oh, it's 1.69. I know exactly where they're going with. Sometimes you can actually see where they're going to go with the problem just because you have experienced with the exam. And you haven't even looked at where you're going to have to use that number, but you already have a feeling of how the number might be used just because of the number they chose in the problem. And that comes, of course, with experience of doing problems. But this is what you need to know for simple harmonic motion. The work-energy theorem is one of the classic concepts that really helps us solve problems. There are different ways to write the work-energy theorem. The most general way to express it is the following, which is that work is equal to the change in kinetic energy plus the change in potential energy. If there is no potential energy terms in the particular condition or situation that you're looking at, then it ends up being that work is simply the change in kinetic energy. this work energy theorem can be applied to many different situations. In one of the contexts, we can imagine that the kinetic energy is equal to 1/2 mv squared. 1/2 mv squared. And the potential energy is equal to mgh. mgh. So m, of course, being the mass, v the velocity, g gravity, and h is the height. So this is one way of writing the equation, and a change, of course, means the difference between the final situation and the initial situation that the object is in. Now let's look at another application to do with electricity. This is a classic question. Here we have a charge, say a large positive charge here. Here's a distance r and a distance r. We have another charge here, plus q. This is position A, this is position B. Here is the question. What is the work done in order to move the charge plus q from position B over to position A? The answer, 0. The reason is that if the distance r is the same, and it is, r is the same on both sides, then it implies something called equipotential lines. And if you have any charge, around a charge there will be equipotential lines, meaning that anywhere there is something at that same distance around the charge, it would have the same reaction to the charge. In other words, if it's a positive charge and you put another positive charge here, well, like charges repel, so the charges would like to move away from each other. And that same desire to move away, or potential to move away, is the same at the identical distance all around the charge. So that would create an equipotential line around the charge. So the potential will be the same at A or at B. So in other words, there's no change in the potential energy at A or B. What about the kinetic energy? Well, if the charge wasn't moving here and we lifted it up and we put it over here, it wasn't moving there. It's not as if we threw it or anything. We picked it up and we put it to another position. So there's no change in kinetic energy and there's no change in potential energy. Therefore, the work done, it doesn't even matter what path you use to go from here to there, the work done is 0. It's like picking up the overhead projector and running around campus and putting it back in the same position. The displacement in the sense of gravity is 0. And the displacement in the sense of electricity, because of an equipotential line, here is 0, so the work done is 0. Here are two other concepts that are favorites for the MCAT exam. The first is conservation of energy. Conservation of energy states that the energy of any mechanical system is constant. In other words, if you were to look at the total energy of a system, for example, an object in a certain position with a certain kinetic energy and a certain potential energy, and you examine it at some other point, then you can look at its kinetic energy and its potential energy, and it will be the same because the total energy is constant. So conservation of energy says that the total energy is conserved. Incidentally, conservation of energy applies to systems that are not being acted upon by external forces. If there is an external force, then there will be work associated with it if the object moves through a distance, because force times displacement is work. And if there is work done because there's an external force, then instead of using the conservation of energy where the total energy is conserved, you would talk about the WorkEnergy Theorem, where work is the sum of the kinetic energy and the potential energy changes. Next, the second law of thermodynamics. The second law of thermodynamics states that the entropy or randomness of the universe increases in any real system. So let's look at an example of this. Consider the following question. Let's say you have two copper bars. Each copper bar is exactly the same size. One copper bar is 100 degrees Celsius. The other copper bar is 50 degrees Celsius. We put them together in contact in a perfectly isolated system. In the end, the temperature of each copper bar is 75 degrees Celsius. Question: what happened to the randomness of the universe? Does it increase, decrease, or stay the same? You may want to pause and consider your answer. The randomness increases. You may say that the total energy of the system will remain the same, because you started at 100 degrees, one was at 50, you ended up at 75 degrees Celsius for both copper bars. So the total energy of the system remained the same. Nothing was lost or gained by the system. Total energy conserved. Randomness? Well, for one, by definition, the randomness will increase in any real system. But let's look at this more specifically. How could you imagine that the randomness of the universe actually increases if we come to a temperature between the two? Well, imagine if you had a split personality. And in your bedroom, half of your bedroom was beautifully immaculate, and the other half of your bedroom was completely messy, with things randomly all over the room, clothes all over the place, etc. Everything thrown on the ground, garbage, and so on. If someone came into your room, they would see a perfectly clean part of your room and the other part of the room incredibly random. Now, what happens if the randomness on one side of the room went onto the other side? So you spread the randomness around the entire room. Would the overall randomness of the universe increase, decrease, or stay the same? Well, I think you would see that it would increase, because you had so much order in part of the room. But if anybody walked into the room, they're just going to say the room is messy. They're not going to say, oh, the messiness is sort of evenly distributed. They're going to say the room is messy. And in other words, more space has been occupied, and therefore more of the universe is random, and therefore entropy has increased. Momentum. The key concepts behind momentum include that mv is a constant, which is to say that mass times velocity is constant. The other concept is that of impulse. Impulse is defined as the instantaneous change in momentum. When we discuss momentum, usually the problems that they like to give you are problems of collisions. There are two types of collisions that they may give you. One is when two objects collide and bounce off each other. That would be called an elastic collision. When two objects collide and stick to one another, that is called an inelastic collision. So they collide, stick to each other, and then they move off in some direction. Either way, whether elastic or inelastic, the motto for collisions is that the momentum before is going to be equal to the momentum after. Now let's look at what would happen for an elastic collision. So two objects hit each other and then bounce off each other. So because there are two objects, we would have two masses, m1 and m2. Now each of those masses would have a different velocity, v1 and v2. So the momentum before would be based on m1 v1 plus m2 v2, and then they collide. So the momentum before would be m1 v1 plus m2 v2. The momentum afterwards would be the same masses, m1 and m2, and each would have a new velocity, v prime and v double prime. So we would have m1 v prime plus m2 v double prime. The key thing to remember about momentum is that these are vectors, meaning you have to keep into account what directions things are occurring. If things are coming in different directions, then one would be coming in the positive direction, the other would be in the negative direction. You would just have to define which is positive, and then you remain consistent throughout the problem. If things are coming in to hit each other at various angles, then you would need to resolve the momentum or momenta into their different y and x components. So it's important to remember that these are vectors. We're going to work out a problem that uses both momentum and conservation of energy. Now let's look at a momentum problem. Consider the following. A projectile, in this case a bullet coming from a gun, a projectile is launched. It has a mass small m and a velocity large v. It is launched at a large mass that's hanging from a string or cord. When the bullet is launched at the mass, this is before the collision, then after the collision we will have the mass and the bullet will be embedded in the mass. So we'll have the large mass plus the small mass as the bullet is embedded in the mass. So it'll hit this and then it would move to the left. It will move with a velocity v. So the question would be either they would give you the velocity of this large mass, or they'll give you the velocity of the bullet, and they'll give you a couple of velocities, but there'll be one unknown. Whatever they require of you in terms of an unknown, it'll be a very simple problem. First of all, you would recognize that this is an inelastic collision. It is inelastic because the two masses will stick together. And in order to work out the equations, we just simply say the momentum before the collision is equal to the momentum after the collision. The momentum before the collision would simply be m times v. So before the collision we have m times v. The momentum of the large mass before the collision is 0 because it's m, large m, times its velocity. Well, it's just hanging by a string, so it has no velocity, so it's 0. So we would have mv plus 0 is equal to the momentum after the collision, which is the sum of the masses of the system times its new small velocity. So this would equal m plus large m small v. And with this equation, whatever they provide as an unknown, you would easily be able to calculate. Now, let's complicate matters a little bit. Let's say that the question is not just what the velocity will be, the initial velocity, but let's say we know that when this mass gets hit by the bullet, it will swing. So let's imagine that the mass is swinging. So we'll draw the result here. So the mass swings to the left. Well, its center of mass is going to rise. The center of mass being here, there, so it's going to rise. And it's going to rise, what we'll say is a height, h. So let's say that the question is, after the bullet hits the mass, and the mass swings, by what height h will the center of mass rise, or will the mass rise? By what height h? What would be the maximum height? For this, we go to conservation of energy. And conservation of energy would tell us that the total energy down here, once the system was moving all together, once it was all together, the total energy down here would equal the total energy up here. Now the second that it has a velocity as a system, soon as it has velocities as a system, therefore it has kinetic energy. Its potential energy at this point, while it's hung by the string, its potential energy is relatively zero. So it has all kinetic energy. When the mass rises to the top, there is an instant when the mass will change directions. In other words, it swings to the top, then it's just about to change directions and start coming down. When it's at its maximum height, for just an instant, it has no velocity, and therefore it has no kinetic energy, because kinetic energy is 1/2 mv squared. So it will have all potential energy, mgh. Therefore, the kinetic energy, once the system starts to move, will be equal to the potential energy when the system is at its highest point. And therefore, we would get the equation using conservation of energy that the kinetic energy down here would be 1/2 m plus m v squared is equal to m plus m gh, which is the potential energy. And of course, these cancel, and we get 1/2 v squared is equal to gh. Once again, you can calculate whatever they provide. By the way, on the MCAT exam, it is quite frequent that they will give you extra data that you don't even need to use for your calculations. That's why it is better to use symbols first before you start plugging in numbers. Reduce to the simplest possible situation before you start plugging in numbers to avoid unnecessary calculations. You could just imagine how messy this could be if you started plugging in masses when you didn't even really need to. One more question. The bullet hits this mass. Everything moves to the left. What work did the bullet do in order to raise the mass a height h? 0. The bullet does no work to raise the mass a height h, because remember, work is force times distance, really displacement, but work is force times distance where the force is in the same direction of the displacement. So this is the force would be acting in this direction, the height h is in that direction, which is 90 degrees, cosine 90 being 0, so the work done would be 0. We are now about to look at the law of torques. I suppose one might say that we're about to do the nuts and bolts of torques. Sorry for that. Anyway, consider this. Here is a nut, and here is my best rendition of a wrench. And I want you to consider the following. Torque forces are turning forces. In fact, if you've had experience turning a nut with a wrench, you'll find that if you tried to turn here, it's very difficult. If you put your hand right there and try to turn, it's very difficult. But as you start moving further from the turning point, because the point about which this whole system turns would be right here, the center of the nut. That's the point about which everything is turning. So that point we call the pivot point. As we go away from the pivot point, along the handle, along the perpendicular distance away from the pivot point, our ability to turn the nut increases. So our turning force increases as we start moving away from the pivot point. Our turning force increases means that our torque force multiplies as we go away from the pivot point. In fact, the torque force is defined as the force applied times the perpendicular distance from the pivot point. So if you maintain the same force, but you start moving away from the pivot point, your torque force increases. Now here's a nut. Let's say that you applied 10,000 newtons of force. 10,000 newtons of force is a tremendous amount of force, and you apply it right at the pivot point. What would the torque force be? 0. Because the torque force is the force applied times the perpendicular distance away from the pivot point. So if you apply all this force at the pivot point, the nut's not going to turn. You might break it, you might cause damage to something, but you're not going to turn it. In order to turn it, you require some distance, torque, some twisting, some turning force, and you have to get away from the pivot point. Otherwise, the torque force would be 0. So now we're going to look at a couple of problems based on torques. We will begin by looking at a simple problem, then we'll look at something more complex. So let's say we have a teeter-totter, and on the teeter-totter we have 3 little children shaped like boxes. And each one of them has a different mass, M1, M2, and M3. So we know what the forces that are here would be, because the force here would be M1G, the weight. The force here would be M2G, and this would be M3G. This is called the fulcrum. It is the point about which the teeter-totter bends in the different directions. The fulcrum is what we would take as our pivot point, the point about which things turn. Now, if this system is at equilibrium, then we say that the sum of clockwise torque forces is equal to the sum of counterclockwise torque forces. So how do we determine when a force is clockwise or counterclockwise? Well, we said that this has a weight, M1G, which points down. This is M2G, that points down. This is M3G, and that points down. So now this, we have to imagine, because it's our pivot point, the point about which things turn, let us imagine this is the center of a clock. And if this were to be the center of a clock, and the clock ticks in this direction, so a clock turns in this direction, therefore only one of these forces is moving in the direction of this marker. Only one force, and that is M3G, is moving in the direction of this marker, which is clockwise. You can clearly see that the other 2 forces, M1G and M2G, are moving in the opposite direction. So M3G is our clockwise torque force. And that would equal to, moving in the counterclockwise direction, would be this. This being the center of our clock, this is moving in the counterclockwise direction. We have M1G and we have M2G moving in that direction. So we get M1G plus M2G. And this is a system in equilibrium. We have the sum of clockwise torque forces equals the sum of counterclockwise torque forces. Now let's complicate the system a little bit. We are now going to look at a problem with torques such that by solving this problem, you will be able to solve essentially any problem they're going to give you about torque forces. So we have a bench. On the bench is a mass. This mass weighs 500 newtons for this mass. The plank is 100 newtons. It is 4 meters long. The question is, what is the weight supported at A and B? First, we're going to have to draw some arrows on our diagram in order to have clear in our minds where the forces are acting. Well, here we have a mass, and so it has its mg acting downwards, and in this case we know it to be 500 newtons. So this is the number 500. We also have the weight of the plank is going to act downwards. The weight of this plank, which we would have to be given that it's uniform. If we know that this is a uniform plank, means that it's shaped evenly over its distance, then the 100 newtons of weight would act at the center of gravity. And for this means that it would act at its center. If it's 4 meters long, it means that at 2 meters in the center, we have what is essentially the downward force, which is the force of the plank, and that is 100 newtons. So we have 100, which is acting right at the center, 500 newtons, which is acting as a consequence of the box. So these forces are acting downwards. Clearly, in order for this not to fall, there has to be forces acting upwards. Just like we saw before, if there's a net force, there will be acceleration. So if this system is in equilibrium, it's not moving, it's just a bench, well then there has to be forces acting upwards. And these forces must be at A and at B in order to prevent this from accelerating downwards. So there are two rules to remember. And with these two rules, you can solve any of the torque force problems that they will give you. One rule is translational equilibrium. And the other rule is rotational equilibrium. These two rules will permit you to solve any of the problems that they will give you. The first one, translational equilibrium, what that tells us is that if you sum all the upward forces, it will equal the sum of all the downward forces. So what are the upward forces? Well, we have as upward forces B acting upwards, and we have A acting upwards. So the sum of upward forces would be A plus B. And that would equal the sum of the downward forces. And the downward forces would simply be the box, 500 newtons, and the plank, 100 newtons, would be our downward forces. So A plus B is equal to 600. So I don't know what A is, and I don't know what B is, but I do know for this system to be in equilibrium, A plus B must equal 600 newtons. Now rotational equilibrium, which is essentially what we saw when we looked at the teeter-totter. And that is that the sum of clockwise torque forces is equal to the sum of counterclockwise torque forces. But one problem. When we looked at the teeter-totter, it was clear where our pivot point was. It was at the fulcrum where things were turning about. And when we looked at the nuts and the wrench, it's clear where things are turning about. But here, nothing's really turning. So then, in this circumstance, we can choose our pivot point. We can choose any single point along the bench as our pivot point. Then we calculate everything from that point. There are a couple of tricks though. If you have two unknowns, then you should choose one of your unknowns as the pivot point. The reason is that we saw that the torque force at the pivot point is always 0. So if you have two unknowns, if you take one unknown as your pivot point, then the torque force at that point is 0, so it eliminates one of your unknowns. Then you only have to deal with the rest. So in this example, let us take A as our pivot point. That will eliminate A as a torque force. Then we're going to look at everything rotating around A. So A becomes the center of our clock. So everything that's clockwise or counterclockwise depends on A being at the center. So A being at our center of our clock, and we're going to look at what moves in the clockwise direction. A being at the center of the clock. So the forces moving in the clockwise directions, we have the 500, which moves in the clockwise direction. 500 times the distance, because the torque force is the force times the distance. So 500 times 1.5 would be part of our clockwise torque force. 500 by 1.5. Then we have plus. Still moving in the clockwise direction, we have 100 times its distance from the pivot point, which would be 2 meters. So we have 100 times 2. And that would equal the sum of our counterclockwise torque forces. Now clearly, still moving in the clockwise direction, B is not in the clockwise direction. It is obviously in the opposite direction. So let's move in the counterclockwise direction around A, and we see that B is indeed in the counterclockwise direction. So the force at B times the distance of B to A, which would be 4. So now we have an equation. So we can solve for B. Once we solve for B, we can solve for A. Just understanding these concepts of translational equilibrium and rotational equilibrium will permit you to solve any of the problems they will give you regarding torque forces. Now let's move on to fluids. Now we will examine fluids. And a fluid is essentially anything that flows. So a fluid may be air, water, or molasses. There are about 5 equations regarding fluids that you absolutely must memorize. Very important equations. The first is that of specific gravity. The specific gravity of a substance is simply the density of that substance over the density of water. Sounds like a simple definition, but this is a commonly used concept on the MCAT exam, that of specific gravity. So it's the density of a substance over the density of water. We will see later why this concept is so important and its application is important. Of course, you should have memorized the density of water, which everyone thinks of 1. But what is the units for that? The units for the density of water is grams per cc, or grams per centimeter cubed, or grams per milliliter. That's all the same. You should also know the density of water in kilograms per meter cubed, because that often commonly comes up on the MCAT exam. You can determine that by dimensional analysis, by looking at the units and converting the units appropriately, or you can memorize that the density of water in kilograms per meter cubed is 1,000 kilograms per meter cubed. The next equation that's very important to memorize is the equation regarding pressure, and that is simply that pressure is force per unit area. So it's the force per unit area. Next, fluids which are static, which means, say that you have a cup of water, or you're looking at a pool or whatever, and you would like to know what is the change of pressure from one position to another position in that fluid. Well, that change in pressure as you go from one spot to another would be dependent upon the density of the fluid, which is symbolized by the Greek letter rho, the density of the fluid, the gravity, because certainly the pressure would be different on Earth as it would be on the moon, so rho g, and on the depth or height that you're moving within the fluid, delta H. Change in pressure is equal to rho g delta H. Very important equation. Next, let us look at the equations of fluids in motion. We will now look at two very important equations that describe fluids in motion. The first is called the continuity equation, and that states that rho V A is constant. That's rho, the density of the fluid, V, the velocity of the fluid, A, the cross-sectional area of the fluid, is a constant. So this is an equation, along with the others, all the others that we've looked at in this series on physics, that must be memorized. Now it's important to understand this is not the same area as in pressure is force per unit area. This is cross-sectional area. For example, if it was a pipe that we were talking about and fluid that's running through the pipes in your apartment or in your home, the cross-sectional area of a pipe would be a circle. If you were to cut the pipe along its length, you would see a circle. It is important for you to know what the cross-sectional area is. Of course, the area of a circle is given by pi r squared, where r is the radius of the circle, pi being 3.14. That, of course, is a basic equation that you are definitely expected to know. The other high school equation is, of course, the circumference of a circle, which is 2 pi r. That also may come in handy. This is the equation of continuity. The other equation is Bernoulli's equation. Bernoulli's equation says that the pressure plus 1/2 rho v squared plus rho gh is a constant. That's the pressure of the fluid plus 1/2 rho the density, v the velocity of the fluid, squared, plus rho gh, the density times g, gravity, times h, the height, is a constant. So these two equations are very important to memorize. The Bernoulli's equation is very simple. Sometimes on the MCAT exam they'll actually give you Bernoulli's equation and ask you to manipulate it or work with it. So, but I suggest still that you still memorize the equation, and it's rather simple to memorize. We're talking about fluids, so you know pressure's involved. Then we have a kinetic energy term. Just like 1/2 mv squared, well, this is 1/2 mv squared over volume because we're talking about fluid. So it's 1/2 rho v squared, very similar. Just like we had potential energy, mgh, well, this is essentially mgh over volume because this is mass over volume. So very similar terms. So let's look at a problem or an application of these terms so that you can feel comfortable about using them. Consider this system of pipes with varying diameters. There are three different diameters, A, B, and C. The fluid is moving through this system in what is called streamline flow, as opposed to a lot of turning, which would be turbulent flow. So as this fluid is moving through the system, we have different cross-sectional areas. Now here's the question. In which one of these containers or areas would we have the highest pressure? You may want to pause and consider your response. Well, to begin with, based on the fact that there are different cross-sectional areas, let's see what happens in the place that has the smallest cross-sectional area, right here at B, where we have the smallest cross-sectional area. Based on the continuity equation, smallest cross-sectional area means the highest velocity in order for this to remain constant, as long as the density remains the same throughout, which means a fluid which does not compress, or an incompressible fluid. So we have the lowest cross-sectional area has the highest velocity. So at B, we have the highest velocity. Then we look at Bernoulli's equation. If we have the highest velocity, if density is more or less constant, but we have the highest velocity, that means we would have the lowest pressure. Because the term for height, overall, the height is going to be equal through this system. so that this term is not important. But if we have the highest velocity, which clearly would be here, based on the continuity equation, then we would have the lowest pressure at B. The highest pressure, therefore, would be at A, where the velocity would be lowest. And one more question. Where would the flow be highest? And flow means volume per unit time. Well, the flow throughout the system would be the same. And this is for an incompressible fluid that is moving as shown, which means streamline flow. Then the flow would be the same throughout the system. Volume per unit time. Here there's a large volume, but it would take a large amount of time to move it. Here's a small volume, which would take a very small amount of time to move, etc. And so the flow throughout the system would be the same. Now let us look at Archimedes' principle. Archimedes' principle states that the buoyancy force on a body immersed in a fluid is equal to the weight in volume of the fluid which is displaced. Now let us apply this information. Let us imagine that there is a glass of water, and in it there is some ice. Well, if you look at a glass of water with some ice, you will notice that the ice not only floats in water, but it actually has a bit of its surface will be above the surface of the liquid water. This is a very unusual feature because most substances, when it goes from liquid to solid, it becomes more dense in the solid form, and therefore it would end up at the bottom. But water is this very unusual substance where when it becomes solid, it actually expands and it actually floats. Now the question is simple. When the ice cube melts, will the surface of the water go up a bit, go down a bit, or remain the same? You may want to consider your response by pausing and then come back. The answer is, it remains the same. And the reason is, this ice cube has a certain weight, and the weight pushes down and pushes aside the liquid water. This ice cube can change shape, become liquid or whatever, but did its weight change? No. And if its weight did not change, then its force to push the liquid water aside cannot increase nor decrease, and therefore the level of the water cannot change. Imagine for a second that you had a bucket of water and you had a big styrofoam thing, and you put this styrofoam thing in your bucket of water. Well, the styrofoam would push aside a certain amount of water. How much water? It could only push aside the amount of water which is equal to the weight of the styrofoam. The styrofoam is applying a force, a weight, and it pushes aside water. It could only push aside the same amount of weight that it has as a force, and then that would be equal to the buoyancy force. Now let's say that we looked at exactly how much water was pushed aside when we put this big styrofoam thing in the water bucket. Now let's say that we took the styrofoam and we squished it and squashed it and squanched it and then put it back in the bucket. Do you think that styrofoam would push aside any more water or any less water? It would be the same amount of water. It doesn't matter that its shape has changed. It will be the same amount of water that will be pushed aside because its weight has not changed. So its ability to push aside water has not changed. There's something else that's important to say, and this brings back the concept of specific gravity. Now, we talked about specific gravity being the density of substance over the density of water. Well, if you have a specific gravity of 1, then you have the same density as water. So if you had something with a specific gravity of 1 and you put it in water, well then it will go below the surface of the water because it's the same density as water. But if you have a specific gravity of, say, 0.9, then the density of the substance must have been less than the density of water, so therefore it would float, which is the case of an ice cube. Now, if you were to be asked what percentage of the substance is below the surface of the water, well, it would just be 90%. So a specific gravity of 0.9 indicates that 90% of the substance would be below the surface of water. That includes the height of the substance. 90% of the height would be below the surface of water. Specific gravity of 0.6 means 60% of the substance would be below the surface of water.